Another day. So here we have a Graseby Controls inverter drive, model number XL7.5 V4B3N. Now the problem with this drive is it comes up with an alarm E001. And on this plate above the bus capacitors back here, that says instant trip. And on the front of the drive where we see that alarm E001, there's also a red LED that comes on when that fault trips. And it's called instant current. So we have a current fault. Now what we're going to do first, before we power this up, we're going to check the IGBT to make sure that it's not shorted. We'll check the IGBT and the three-phase bridge. There's two fuses in here. We'll check to see if they're blown open, and then we'll apply 460 volts, three-phase AC to L1, L2, and L3, and we'll see what we have. Now, I'm worried about running this drive because of that instant current, but it does appear to shut down when it gets that instant trip fault. Now on the front of the drive, we'll see this in a little bit, there's a start and a stop switch. And the way I'm interpreting these connections here, this drive is set up to run from that keypad. The stop terminal is jumped out right here. So it looks like we're running from that keypad. But again, like I said, I'm a little bit worried about running this drive with that instant current alarm. But let's check our IGBT and three-phase bridge and fuses real quick. I'm going to pull this safety plate off. It also has the alarm codes, the fault codes written on it. But this plate right here keeps our fingers off of those bus capacitors. It's common sense not to get across those, but sometimes when you're around these cabinets, going inside a cabinet or something like that, it's real easy to get on something that's live. All right. Try and set this where y'all can see it. Might take a little bit of work in there. Down here. Can y'all see that? If I turn that light on. I don't know if you can see it, but I'll read it to you. Okay, I'm going to take our black lead and put on bus plus, and I'm going to go over here to L1. And we have a diode drop of 0.539 volts. Here's red lead on L2, 0.539 volts. Red lead on L3, 0.539 volt diode drop. That's good. Now I'm going to go over here to T1. This is where the motor connects. Get on it, come on. There we go. 0.421 volt diode drop with the red lead on T1. Red lead on T2. 0.421 volt diode drop. Red lead on T3. Black lead on plus bus. 0.421 volt diode drop. Now we're going to take our red lead and put on bus ground. Black lead on L1, 0.394 volt diode drop. Black lead on L2, 0.394 volt diode drop. Black lead on L3. Red lead on bus ground. Oop, get on there. 0.394 volt diode drop. Now black lead over here on T1. Get on there. Come on. There you go. 0.421 volt diode drop. Black lead on T2. 0.421 volt diode drop. Black lead on T3. Red lead on bus ground. 0.422 volt diode drop. No one is shorted nor open. I'm going to put that plate back on those bus capacitors. See right here the alarm codes. That's really convenient right there. I went on the internet trying to find a data sheet on this drive, and I could not find one. I'm sure it's out there someplace in book form in the real world, but on the internet I could not find one. I'm usually pretty good about finding data sheets on the internet, but this one did not exist. But it's very well put together as far as information on the drive goes. The instant current LED and the other alarms that were possible are on the front of the drive, indicated by LEDs. On hands, on left hand, you can do it. There we go. Okay, now we are ready to apply the line voltage to L1, L2, and L3. The data plate over here says input 460 volts, 3-phase, 60 hertz. All right, let me go turn this drive on. We'll see what we get. Okay, let's apply 460 volts AC, 3-phase to L1, L2, and L3. All right, we have our DC bus LED, charge LED turned on. Down here on this side of the board is another red LED named charge. And look at this. This is interesting. This LED right here should be off. That firing channel LED indicates that this channel has a problem. Now all these LEDs, there's 6 firing channels, and the LEDs indicate that that firing channel is turned on. That LED should be off. This looks like that is the problem with this drive. This one firing channel has a problem. That would create a short circuit condition if one of the IGBTs is turned on all the time. Say for instance that's the low side IGBT, and the low side IGBT is turned on all the time, and then you turn on its complement, the high side IGBT, you would have too much current flow through those high side, low side IGBTs, and that would trip the drive with instant current fault. So I believe there is our problem. Now the nice thing about this drive is we have 6 firing channels, 5 others that we can compare this one channel to. Let's go see if we can find something wrong in that firing channel. Let me power down. We'll get unplugged from the wall. We'll let that DC bus discharge. First thing we're going to do is put our probes on the gate emitter wires of the firing channel. Now, I've got my meter set to diode test mode, and here's the good channel. And we have 0.295 volt diode drop. And look, I turned on that LED for that firing channel. Now let's do the same thing for the bad firing channel. All right, that's open. I've opened from gate emitter in the firing channel. Let's go to the third one. This is a good firing channel, or at least one that's not turned on. Look, 0.298, and I turned on the LED. So there is definitely something wrong with this firing channel. I'm going to have to figure out how to get this thing apart, because we're going to have to go into that firing channel and find out what the problem is. It's the first time I've ever worked on one of these drives, so I don't know how it comes apart. A bunch of wires. Well, can't be any harder than the worst thing we've ever worked on. Let's go in. Where to begin? Well, we're going to have to draw some pictures. We're going to have to draw some pictures of where all these wires go. So when we go to put this drive back together after our repair, we'll get everything wired up right. That's half the battle on most of this stuff, is getting it back together correctly. Let me draw some pictures, and I'll come back. You don't need to see me draw. My drawings, if I could go back to kindergarten and learn how to draw again. Okay, we'll see you in a little bit. Let's disconnect the front panel. Okay. Underneath here, I don't know if you can see it, but this is where the gate emitter connectors come up to, and I've got this drawn out so I won't get them mixed up. I'm going to disconnect these wires right here from the IGBT. Okay, so I'll do this wire over here. Connector from the transformer. I'll do that one. See if we can lift this up any farther. We're downstairs. Here's the three-phase bridge. Here's the IGBT. Well, there's the bus capacitors. Let me get a picture of that. Get a picture of this down here. We've got two connectors over there we're going to have to undo. Okay. Okay. Now, I can figure out a way to unbolt this board right here. There's some hex nut screws over here, and then I got to undo the bus. Some terminals over here. I've never seen that type of terminal before. I have to undo those. Undo these wires. Okay. A little bit more work to do. Mark these two wires with dots so we know which way to put them back on. I want to think those are thermal wires. That undone. So do this connector under here. That's J11. And we got to undo these two bus wires right here. Let's make sure there's no voltage on that red and black wire right there. I know the bus is discharged, but we'd like to live another day. Alright, 0 volts DC on the red and black wire. Good, we can undo those two terminals right there. Okay, I think all I've got to do is undo these two nuts right here. And that should allow us to bring the firing board and the control board out of the housing. Don't have a whole lot of room to get in here. There we go. Come on, don't be stubborn. That one's going to take the wrench to get all the way off. The other one I could spin off with my fingers. That should be it. Yeah, there we go. Not everybody. Let's see. Yes, we are free. All right. Here's the connectors of the firing channels that go to the IGBT. Mind the frame? Right here. That's your gate emitter connectors of the 6 firing channels. Okay, we'll move the power base out of the way, and then we'll take a look at that bad firing channel. Hopefully we can find the problem. We'll see. Let's remove this top board so it's not in our way while we're looking at that bad firing channel. Now we're missing 2 nuts right here. We're going to have to replace those. We'll take these 2 off right here. That one's cracked. Wonder how that happened. There we go. Now we have a clear view of our firing channels. This is the bad one. The other 5 are supposedly good. Look at all the parts in that firing channel. See if we can get closer. We're going to take our meter and go through all of the devices in these firing channels and make sure that they're good. I'll have to read to you what the meter says, because as close as we're going to get, I'm not going to be able to get the meter in there. Okay. Set my meter to diode test mode. We're going to take a look at these Zener diodes first. Let's go to the good firing channel. 0.731. Here's the next one. 0.733. Those 2 Zener diodes. Here's the bad firing channel. Get on there. 0.729. That's a good Zener diode. 0.732. That's a good Zener diode. Let's go on the gate emitter connectors while we're disconnected from the IGBT and see what we get. There we got again 0.297 volt diode drop across that connector. And that one's open. We have OL in the display of the meter. We'll check these resistors here. Go to resistance mode. There's a negative value right there. -7, -69. It looks like I'm charging up a capacitor. It's going to swing back the other way. There we go. We're at 12.5 K. Still rising. Still rising. 16 K. And still rising. Let's go to this one. There's 32.81 K right off the bat. No charging of the capacitor. Let's go back to this one and see at what point it finally stops charging that capacitor. 17 K, 18 K, 19 K, 20 K, slowing down, 21 K, 22 K. 23 K. There's tau. RC network here someplace. Still rising. Okay. I wonder what value that resistor is. Let's check this one. In the good firing channel we have 67.5 ohms. Let's go over here to the bad firing channel. Get on there. Huh, that's interesting. 630K and rising. 650K, 680K, 690K, 700K. Okay, let's check this power resistor right here. It's 385K. Let's go over here to this one. 402K. We're going to have to flip the board over and we shall check these transistors. There's 2 right there, 3 right here. There's 2 right there and 3 right there. I'm not sure what types of transistors they are, but we'll figure it out. Flip the board over, make sure I'm still back in the picture here. Okay. It looks like the outline of the 2 transistors in the good firing channel right here, and the 2 transistors in the bad firing channel right there. So let's just set our meter to diode test mode. Okay, that must be NPN. Reverse my leads. Oh, that's interesting. There we go. There's a voltage diode drop. 0.704. Let's check this one over here. 0.688. Huh. Swap leads here. Nope. Okay, from here I have 2.03 volt diode drop. Let's go check this one. That one's open. Not sure what type of transistor that is. Usually with the transistor you have diode drops from base to emitter and base to collector. But I only had one diode drop in the 0.7 range. Okay, there's 0.718 right there on the second transistor. 0.703 on the second transistor of the bad firing channel. That one's open. Let's see what we got here. Okay, from here to here, that's open. Okay, there I have 1.326. Let's go to this one. And that one's open. It's very interesting. I'm going to have to find out what those 2 transistors are. But before we do that, let's check the ones up here, the 3 that were side by side. Okay, they're right there. Okay, there they are. All right, there's a transistor that measures right. Let's go up here and check these guys. 0.725, 0.720, 0.730, 0.725, that's the second one. 0.728, 0.722, 0.733, 0.729, 0.734, 0.729. So it appears that the three transistors in both firing channels up here are good. There's something going on down here with these. Let's go across that capacitor. There's a 10 ohm capacitor right there. 1.673, 1.650. They're pretty close together. Find out what these two transistors are down here. Let's see if we can get a good measurement on those guys. These two transistors right here. See if I can get part numbers off of them. I'll put out the old magnifying glass. Here are the two transistors. They're Darlington. That's why we had that odd reading. We'll go back in there and measure them again. But in the good firing channel, we had about 1.3 volt diode drop from base to collector, and in the bad firing channel, that was open. We had good diode drops in both channels from emitter to base. So the part numbers, 2N6426, that's NPN Darlington transistor, and MPSA64, that's PNP Darlington transistor. So let's pull that board back over here and we'll check those two Darlington transistors again in the good firing channel and the bad firing channel. Turn my meter around so it's upright. There, can y'all see that? I can't ever tell because there's a lot of glare in this shop from the overhead fluorescent lights. Okay, there we go. Now let's make sure we're on the right path here. Okay, good firing channel, bad firing channel. Good, 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 bad. Bad. Okay, check the good Darlington transistor first. I believe this was the PNP transistor. Alright, we have a diode drop of 0.703 volt. Let's go to the bad firing channel. Base to emitter, 0.688 volt diode drop. Now let's go base collector, the good channel. There's 1.326 volt diode drop. That's your Darlington. And here's the bad firing channel. And that one's open. We have OL in the display. Now we'll check the NPN Darlington transistor. Base to emitter, the good firing channel, 0.718 volt diode drop. Here's the bad firing channel, 0.703 volt diode drop. Here's the good NPN Darlington base to collector, 1.33, is that 2.5? Yeah, I'm upside down, 1.335 volt diode drop. Here's the bad Darlington. Okay, that's base to collector, it's open. So those two Darlington transistors are bad. Now I don't have that part number here. I'm going to have to order that part, those two transistors. And that means we'll have to finish this repair some other day. But we know what the problem is. We know that these two Darlington transistors are the cause of the failure in that firing channel. There we go. Repair for another day. Okay. Well, we'll see you next time. We'll see you when the parts come in. Have a good day, all. Have a good day. We'll try to do the same here. Here we have two new PNP and NPN Darlington transistors, and here are the two bad NPN and Darlington transistors from the bad firing channel. Now this part number is MPSA64. That's the PNP Darlington transistor. And this part number is 2N6426. That's the NPN Darlington transistor. Let's check these with our digital multimeter set to diode test mode. Let's see what a good one looks like. Now here's the PNP Darlington transistor. Black lead on the base, red lead on the emitter, and we have two diode drops there, 1.334. We have two because the emitters are tied together. There's two emitter base connections in a Darlington. Now here's base to collector. We have 0.730 volt diode drop. Let's go over here to the NPN Darlington transistor. Red lead on the base, black lead on the emitter. Again, we have two diode drops, 1.319. That's because we're testing across two base emitter junctions. Here's base to collector, 0.725 volt diode drop. Now we'll look at the bad ones, the two bad transistors. We'll move these good transistors out of the way and bring in our two bad transistors. Bring these down a little bit. Alright, now we'll test the two bad transistors. Here's the PNP Darlington transistor. Let me turn it around so the flat side is face down. It won't roll around as bad on us. Okay. Here's base emitter. Base with the black lead, emitter with the red lead. That's open. There's the problem with that transistor. Let's go base collector. We have a good base collector diode drop, 0.688. It's a little bit low compared to those two good ones. Now, let's check the NPN Darlington transistor. Red lead on the base, black lead on the emitter. That junction is open. Now let's go base to collector. Moving the black lead to the collector. And we have a good voltage diode drop of 0.702. It's bouncing around a little bit there. There, it's stabilized. Okay, so the base emitter junctions on both those transistors have opened up. Now we got the two new Darlington transistors in, but we still haven't got the IGBT. So it's going to be a few more days before that we get that. But now let's use the oscilloscope to test these transistors. Now this is going to be fascinating right here. I don't know if y'all have seen my video of this, what I call the magic box tester. But you get to see with the oscilloscope the waveforms of base emitter, base collector, and collector emitter. Now, I want to think that this at one time was called a Huntron Tracker, or a signal tracer. No, not signal tracer, that's not the right word for it, but I want to say a Huntron Tracker for some reason. But I'll provide a link to the video so that you can make one of these. All right, let's move the camera. We'll get testing these with the oscilloscope. Here's our magic box tester that allows us to test diodes and transistors using an oscilloscope. And its outputs go to the two-channel inputs of that oscilloscope right there. We have an X and a Y output from the magic box tester. X goes to channel 1, Y goes to channel 2. Now, right now, we have no connection to the probes, and this is what a waveform would look like if you had an open circuit. Let's short the red and black wires together, and there is what we would have if we had a short circuit. Now I'm going to use clip leads connected to the red and black probes so that we can clip on to the transistors. The first thing we're going to look at is the PNP Darlington transistor. So let's take our black lead and put it on the emitter. Let's take and put our red lead on the base. And there's our waveform from base to emitter. Now we'll take the black lead and move it to the collector. There's our base collector waveform. Now, let's move the red lead to the emitter. There's collector emitter waveform. Now let's get close to that oscilloscope and we'll test the other transistors, the other good Darlington transistor and the two bad Darlington transistors from that bad firing channel in that drive. We'll disconnect here. Set that over there. We'll move the movie camera closer to that oscilloscope. Here's an open circuit. The probes are not touching each other. Let's look at a short circuit. I've just touched the black and red probe together. They're shorted together, and this is what a short circuit would look like. Hey, real quick, let me grab a resistor and I'll show you what resistance looks like if you have a little bit of resistance in your circuit. Here's a 10 kilo ohm resistor. There's 10 kilo ohms. You see how we're not open and we're not shorted. We're in between. That's cool. So you can check resistors with this gadget right here. I imagine you could check capacitors and inductors too. We'll have to do that some other time. Let's take a look. Here is the NPN Darlington transistor. Okay, I'm going to put the red lead on the base and the black lead on the emitter. There's our base emitter waveform for the NPN Darlington transistor. Moving the black lead to the collector. There's our base collector waveform. Now the polarity doesn't matter. I just like to stay consistent by putting the red lead on the base if I can. Now let's move the red lead to the emitter. And there is our collector emitter waveform. for the NPN Darlington transistor. Now the fun part, we're going to look at the bad devices. Okay, here's the bad PNP Darlington transistor, MPSA 64. Red lead on the base, black lead on the emitter. And look at that. That's exactly what we saw with our digital multimeter. Set the diode test mode that the base emitter was open. Now we'll move the black lead to the collector. There's our base collector waveform. Looks a little bit different from a good one, doesn't it? Alright, let's look at the bad NPN Darlington transistor. And it is the red lead on the base, the black lead on the emitter. And again, base emitter is open. Moving the black lead to the collector. And there is our base collector waveform. Looks a little bit different from the good one. Moving the red lead to the emitter. And here we have collector to emitter is open. I'll tell you what we'll do. Let's see what a standard NPN transistor or PNP transistor would look like. Not Darlington, just your standard NPN or PNP transistor looks like. Let me go find one. I'll be right back. Here's an NTE 159. Red lead on the base, black lead on the emitter. Okay. Red lead on the base, black lead on the collector. Okay, moving from base to emitter with the red lead. And that is a PNP transistor waveform. Now, wasn't that fascinating to see the waveforms of our transistors using that magic box tester? I'll provide a link to my video on this magic box tester, and you can make one for yourself. It's a handy tool to have in your toolbox. All right, there we go.